Today we're going to look at how we can solve exponential and logarithmic equations. And I've already written two examples of exponential equations. 3 to the x equals 20 is an exponential equation. 2 to the 5x equals 64 is an exponential equation. And although we didn't define it, the one-to-one property or base exponent property of exponential equations, we did use the idea in a previous session. And that base exponent property says that if we have a to the x equals a to the y, notice the bases are the same, then this is true if and only if x is equal to y. So if this is a true statement, if we have the same base, then the exponents are equal. So if I have the exponential equation 2 to the 5x equals 2 to the 6th, this is true if and only if 5x equals 6. So it would be true for the value when x is equal to 6/5. Using that same idea, we can go back and look at the equation 2 to the 5x equals 64. And using the idea that if we have the same base, it's true if and only if the exponents are equal to each other. Let me move this a little bit out of the way. Well, I can rewrite 64 as a base of 2. That's 2 to the 5x. And 64 is 2 to the 6th power. So in this case, this is true when x equals 6/5. If the bases are the same, we can set the exponents equal to each other and solve. You could also, I'm not going to do it because of the limitations I have with this app. What we could do is put 2 to the 5x in y1 and 64 in y2 and see where those two functions or where those two graphs intersect each other, and that would also give us a solution. All right, let's look at a different equation. Let's say I had 5 to the 4x minus 7. 4x minus 7 equals 125. Well, the first thing we want to do is see if we are able to rewrite this equation so that I have the same base on both sides. And we can see that 125 can be rewritten with the base of 5, and that's 5 cubed. So we can solve this equation by setting 4x minus 7 equal to 3. Add 7 to both sides, and divide by 4. And we always reduce the fraction to simplest terms. So in this case, x equals 5/2. All right, we've already seen that a to the x equals a to the y if and only if x equals y. Well, we have a very similar truth for logarithms. First of all, let me state that m has to be greater than 0, n has to be greater than 0, and a is greater than 0, and it cannot be 1. Part of the definition of a logarithm. And this property, the one-to-one property for logarithms, or sometimes the property of logarithmic equality, if we have the log base a of m, that equals the log base a of n, if and only if m equals to n. So we can use this property as well, and we can use this property when we solve some exponential equations. For instance, we looked earlier and said that 3 to the x equals 20 is an exponential equation, and we want to solve it for x. Now, one way that you could do that is put 3 to the x in y1 and 20 in y2 and find that point of intersection. That's a way that you can do it if you have a graphing calculator. But that may not always be the case. So what we want to do to solve this is either take the logarithm, the common log of both sides, or the natural log of both sides. You'll get the same answer whichever way we go, but we can take the common log of both sides or the natural log of both sides. And if I do that, I'll have the log, I usually just go ahead and do the common log, of 3 to the x equals the log of 20. And we know from our property of logarithms that we can rewrite this as x times the log of 3 equals the log of 20. And then divide both sides by the log of 3. So x is equal to the log of 20 divided by the log of 3. And if we put that into our calculator, that's an exact answer. If we put this into our calculator, and be sure when you put it in the calculator, it's going to come up log and it'll open a parenthesis. Be sure that you close this parenthesis around 20 before you put in the division sign. This is approximately 2.7268. Be sure that that's what you get when you plug it into your calculator. All right, let's look at this one. 84 to the x equals 70. First thing I want to check, can I rewrite those with the same base? And we cannot. So we're going to take the log of both sides. And when I do that, I'm just going to go ahead and move the x to the front because I can do that when I take the log. Remember, we saw that in this previous problem. And that equals the log of 70. So if I divide both sides by log of 84, we get the log of 70 divided by the log of 84. And you can use the natural log if you prefer. The only time that you want to definitely use the common log is if you're looking at a base of 10. But here, this is your exact answer, the log of 70 divided by the log of 84. If we put it into the calculator, we get that that is approximately, and remember, close the parenthesis in the numerator before you put in the division sign, 0.9589. It's approximately 0.9589 or 0.959. That's your approximate answer. And unless we're told differently, you can round to 3 decimal places because that is what you would round to if you were taking calculus, unless it says something different, unless your instructions are different than that. All right, let's look at another one. This one is a little bit different. We get 10 to the negative x equals 5 to the 2x. Now I have different bases. I have variables in both exponents. It won't really do me any good. There's no way that I can rewrite that with the same base. Now let's think about this. With 2 different bases and variables in the exponent on both sides, let's see what happens if we take the log of both sides. Well, we'll have negative x times the log of 10 is equal to 2x times the log of 5. Well, the log of 10, hopefully you remember, is simply 1, and we get negative x equals 2x times the log of 5. And if I divide both sides by 2x, we get negative 1/2 equals the log of 5. And if we plug that into our calculator, that's not a true statement. So something else is going on here. Let's go back and look at our original problem. 10 to the negative x equals 5 to the 2x. Well, the only way that this can be a true statement is if x equals 0. Because 10 to the 0 is 1, and 5 to the 0 is 1. So in this case, notice this is not a true statement, not true. But if we go back and reconsider, if x is 0, then we do have a true statement. Okay, here I have another problem. 100e to the 0.08t equals 2500. In a situation like this, the first thing you want to do is isolate the terms with the exponent if you can, so that that's all we have here. So I'm going to divide both sides by 100. Let me change this color. Let's do this. So that I just have e to the 0.08t on one side. I'd rather not have, if I can figure out a way, I don't want a constant in front of that. So let me go back. So we have e to the 0.08t equals 25. Now in this case, since I have the base of e, I'm going to take the natural log of both sides. So we'll have 0.08t times the natural log of e equals the natural log of 25. Well, the natural log of e is simply 1, and we have 0.08t equals the natural log of 25. We can divide both sides by 800ths. And t, this would be your exact answer, but your approximate answer is going to be about 40 point, let me look at it again. The natural log of 25 divided by 0.08 is 40.236. If we round it to 3 decimal places, it's about 40.236. Okay, we'll do one more. Remember, since we have the base of e, we can use the natural log. You can always use the natural log. Unless you had a base of 10, then you probably want to use a common log. But let's take the natural log of both sides. So we have t times the natural log of e equals the natural log of 1,000. Remember, the natural log of e is always 1. So t is simply equal to the natural log of 1,000, which is approximately, just plug that into your calculator, and you should get that that is approximately 6.908. Okay, here's another one. Notice there's no way that we can get the same base on both sides. So we're going to take the log of both sides. So when I do that, I'm going to have this exponent moves to the front. We'll have the log of 4 equals negative x times the log of 3. Now this looks different than anything that we've seen before. Notice I took the log of both sides first. I didn't show that. Let me show that in a different color. We took the log here and the log here, and that moved the exponents to the front. Now I'm going to distribute the log of 4, so we'll have x times the log of 4 plus 3 times the log of 4 equals a negative x log of 3. Now let's group the terms that have x together on one side. So I'll add x log of 3 to the left side and subtract 3 log of 4 from both sides. Now we've got an equation we can solve. I'm going to factor out the x, and we'll have the log of 4 plus the log of 3 equals negative 3 times the log of 4. And to solve for x, we simply divide both sides by the log of 4 plus the log of 3. And notice I put this denominator in parentheses because when you plug this into your calculator, not only do you need to remember to close the parentheses here and here, you also need to have the entire denominator in parentheses. And in the denominator, you're also going to have parentheses around these that you have to close. And when we plug this into the calculator, if you do it correctly, you should get approximately a negative 1.6737. But it's very important that you close out parentheses where you need to. The only one that you could possibly leave off is this last one. But you have to start your parentheses in the denominator to include the entire denominator. Okay, let's do one more like this. I'm going to take the log of both sides, so just to be sure we all understand, I'm going to add this in red. I'm going to take the log here and the log here. Take the log of both sides, which allows me to rewrite this as 2x minus 1 times the log of 3. You can use the natural log, equals x times the log of 5. Distribute the log of 3 on the left. We'll have 2x log of 3 minus the log of 3 equals x log of 5. Now we'll group the terms with x's together. So 2x log of 3 minus x log of 5. And then add log of 3 to both sides. Notice I cannot combine 2x log of 3 and x log of 5 because I have different numbers here. Those are not the same. If they were the same, then we could combine them. But what I can do is factor out an x. And we'll have twice the log of 3 minus the log of 5 equals the log of 3. And to solve this for x, I'm going to divide both sides by 2 log of 3 minus the log of 5. So we'll have the log of 3 divided by twice the log of 3 minus the log of 5. Again, I'll put this in parentheses to remind us. And when you plug that into your calculator, being careful of your parentheses, you should get x is approximately 1.869. Now we want to look at how we can solve logarithmic equations. Here I have log base 3 of x equals negative 2. Well, in order to solve this one, we can simply rewrite it as an exponential equation. 3 to the negative 2 equals x, and x is 1 over 3 squared, or 1/9. That one's pretty easy to solve. Let's look at one more that's simple like this. Log base 5 of x equals 4. If I rewrite this as an exponential equation, it becomes 5 to the 4th equals x. Really, that's 5 squared squared. 5 squared is 25. 25 squared is 625. Oops. 625 equals x. Now, obviously, things don't always stay quite as simple as those first two that we just rewrote in exponential form. We will get to that point where we rewrite it in exponential form, but let's look at this particular problem. We had some properties of logarithms that said if I add and the bases are the same, then I can rewrite that as the log base, and I don't even have to put base 10 because it's base 10, it's understood that the log, this becomes the log of x times x plus 3 equals 1. We said it was base 10, so I could rewrite this as an exponential equation, and we could say that 10 to the first power is equal to x times x plus 3. Well, I'm going to flip them here. We're going to have x squared and distribute plus 3x equals 10. And x squared plus 3x minus 10 equals 0. And here we're going to factor. And to factor this, we get x and the factors of negative 10 that would add together to give me a positive 3 or plus 5 and minus 2. So x equals negative 5 and x equals 2. Now here we have to go back and check and see in our original equation if these make sense. If I plug in a 2, we need to see if we could get a true statement. We'd have the log base 10 of 2 plus the log base 10 of 5 equals 1. Well, we'd have the log base 10 of 2 times 5, which is 10, equals 1, and that's a true statement. But what we really want to check is here, when we have this negative value. If I plug in a negative 5 for x right here, it doesn't work because this has to be greater than 0. So this is called an extraneous solution. It's an extra solution that does not work. And basically, all you have to do is go back and make sure that you're going to get a positive number here and here when you plug in the values that you got. So here the solution is simply x equals 2. Okay, let's do another one like this. I want to give you plenty of examples so that you should have plenty to help you when you get ready to do your homework. All right, I can rewrite this as the log base 2 of x plus 1 times x minus 1 is equal to 3. And x plus 1 times x minus 1 is x squared minus 1, the difference of squares. Now I can rewrite this as an exponential equation. 2 cubed equals x squared minus 1. And 2 cubed is 8. Okay, I'm going to let these switch sides, x squared minus 1, just my preference. You don't have to do this. If we add 1 to both sides, we get x squared equals 9. And generally, we would say that x equals plus or minus 3. But if I plug in a negative 3 in either one of these, we get a negative number. So our solution is simply x equals positive 3. It cannot be equal to a negative 3. All right, now this problem is a little bit different in that I am subtracting these logs with the same base instead of adding. So when we subtract logs with the same base, we can rewrite this as division from that last section that we just did. All right, so now I want to rewrite this so I no longer have logarithms. I can rewrite this as an exponential equation. We'll get 8 squared equals x plus 1 over x, or I'm just going to go this way, just my preference, you don't have to change it, equals 64. Now I can multiply both sides of this equation by x to get rid of this x in the denominator. And that's going to give me x plus 1 equals 64x. And if I subtract x from both sides, we get 1 equals 63x. So x equals 1 over 63. And that will not give me a negative number in either of these values. So this is the solution. But notice the difference here was I was subtracting, which means that converts to division because a logarithm is an exponent. And when we divide by exponents, we end up subtracting those exponents. Okay, one last problem. Notice here we have logs on both sides. On the left side, I'm going to combine, just like I did on the last problem. We'll have the log of x plus 8 over x plus 1 equals the log of 6. If we go back to those very first problems we worked, we said if we had a log with the same base equal to each other, then this part was equal. Base 10, so both sides have log base 10, so I can set x plus 8 over x plus 1 equal to 6. Now it's just algebraically solving this equation. I'll multiply both sides by x plus 1 to get rid of the complex fraction on the left-hand side. And when we do that, we're going to have x plus 8 equals 6x plus 6. Subtract x from both sides. Subtract 6 from both sides. And x equals 2/5. Right? We won't get a negative number when I plug 2/5 in either here or here. So this is the correct solution. All right, this is going to be assignment number 5 for this quarter, and it is on page 365. And I want you to do 4 to 60 every fourth. Do every fourth problem starting with 4, so that's 4, 8, 12, 16. You can get the rest of those.